Okay, what we're going to do in this vodcast is expand on what we were talking about in the last vodcast with orbitals. And again, orbitals can be a little bit confusing, so let's just do a little bit of review. When you think of orbitals, you want to think of regions where the electron are located. There are four types of orbitals. There's s orbitals, p orbitals, d orbitals, and f orbitals. Each orbital type has a certain number of each orbital. So in other words, there's only one s orbital, there's 3 p's, there's 5 d's, and there's 7 f's. And you also want to remember that each orbital can hold 2 electrons. So since there's only one s orbital, it can only hold 2 electrons. Since there's 3 p orbitals, they can hold 6 electrons. The d's can hold 10, and the f's can hold 14. So when you're counting up orbitals, you want to think of it in terms of the orbital type, how many of each orbital there are. They can each hold 2, and you want to total it up. Alright, some people like to think of it in like this. Like if you have your nucleus, they want to picture those energy levels. So they want to picture those rings around the atom. And then what they do is they think, alright, the first energy level has one s orbital and it can hold 2 electrons. The second energy level has one s orbital and then 1, 2, 3 p orbitals. So 1, 2, 3, 4, 5, 6, 7, 8 electrons. The third energy level has the s's, or the s, the 3 p's, and then the 5 d's. So 1, 2, 3, 4, 5. Now, this is fine if you want to think of it this way to count up electrons. Just realize that's not what the atom looks like. These orbitals are regions. So the s orbital would be a spherical region. The p orbitals would be dumbbell-shaped regions. And then the d orbitals are their dumbbell and donut shape, so it goes on from there. So you can kind of see why we don't draw pictures of the atom using orbitals. So people can think of it in different ways. Alright, so let's start doing what we call electron configurations. What an electron configuration is a notation to tell you where each electron in the atom is placed. And it's based on a few principles. And we're going to go through a couple of them right here. Alright, the first one we want to go over is called the off-ball principle. The off-ball principle basically says that as you add electrons to the atom, they always fill the lowest energy level first. So what I'm going to do here is I'm just going to draw a diagram. And I'm going to draw 1, 2, 3. And what that represents is the energy level. So the first energy level, again, I'm going to draw that box to represent the orbital, and that's the first energy level, the s orbital. The second energy level has the second energy level. It's got one s orbital, and we said that it has 3 p orbitals, so those are the second energy level p orbitals. The third energy level, it has an s, so the third energy level an s. It's got its p's, so the 3 p orbitals in the third energy level, etc. So if you're going to add, say, 4 electrons to the atom, or I'm sorry, 4 electrons to the atom, we would be talking about the beryllium atom. So the first 2 electrons, remember that these symbols, I'm using that as one electron and that as the other. So 1, 2, 3, 4. So you always add the electrons to the lowest possible energy level first. As we move up, that's representing more energy. So the 2s orbital has more energy than the 1s. The 2 p's have more than the 2 s's. The 3 s's, the 3 p's, etc. So again, the off-ball principle says as you add electrons to the orbitals, or as you add electrons to the atoms, they fill the lowest energy levels first. Okay, the next rule that we're going to talk about we call Hund's rule. And this is sometimes referred to as the bus seat rule. The idea being that as you load onto a bus, people always sit single seats first before they double up. So Hund's rule says as electrons fill degenerate orbitals, and that's orbitals of the same energy, they fit one electron per orbital before pairing up. So in our example, let's say we have our 1s, let's say we have our 2s, and then we have our 3 p orbitals in the second energy level. And let's say we're talking about an atom with 7 electrons. So again, according to the off-ball principle, we'll put 2 in that orbital. The next energy level up, or the next higher energy, is the s orbital, so we'll put 2 in there. These p orbitals have the same energy, so they're degenerate orbitals. So we said we're going to add 7 electrons, so we have 3 to go. So we would put 1 in that orbital, 1 in that orbital, and 1 in that orbital. If we were going to add an 8th electron, we would put that 8th one there, and then there, and then there. You could just as easily have paired up that one, then that one, then that one. It doesn't matter which order you go in, as long as you put 1 in each of the p orbitals and then pair them up. So that's what we refer to as Hund's rule, which is oftentimes called the bus seat rule. So what we're going to do is basically do what we just did there. We're going to draw these things that we call energy diagrams. And what they are diagrams representing the orbitals in the energy levels as you put electrons into the atom. So I'm just drawing each energy level with the orbital type and the number of each orbital. The next one would be the 3Ds, but we're going to add in a little exception then. So again, let's put 15 electrons into this orbital diagram. So according to the off-ball principle, we're going to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So if we were going to count up paired electrons, we have 1, 2, 3, 4, 5, 6 orbitals with paired electrons, and we have 3 orbitals with unpaired electrons. That's going to be important for us when we start talking about bonding. Okay. What you can also do is do what we call block diagrams. Now all a block diagram is that diagram that we drew earlier, just horizontally. So you would have your 1s, your 2s, your 3, whoops, I knew that was going to happen, your 3, 2 p's, the next would be 3s, and then your 3 p's, etc. Alright, so what this now leads up to is what we refer to as electron configurations. And electron configurations are, like we said in the beginning, designations of where the electrons are added. So for example, if we were talking about an atom with 15 electrons, its electron configuration would be 1s2, 2s2, 2p6, 3s2, let's see, 2, 4, 6, 12, what did I say, 15 electrons, 3p3. And obviously I'm going to show you how to do this. What it means is that the first energy level has an s orbital with 2 electrons. The second energy level has an s orbital with 2 electrons. The second energy level also has a p orbital with 6 electrons. Third energy level, s orbital with 2 electrons. third energy level p orbital with 3 electrons. So the electron configuration, you list the energy level, the orbital type, how many electrons it's holding, until you get to the total number of electrons. Now, to make this counting a lot easier, what we're going to do is use the periodic table. So if you picture the top of the periodic table, in other words, if you remember it goes down here further like this, and you've got all your blocks down here. So what I'm looking at is the top part of the periodic table. Starting with hydrogen, remember the periodic table, the horizontal rows represent the energy level. So that represents the first energy level, that represents the second, that represents the third, etc. So in the first energy level, what we do is we break it up into the blocks. So we've got a block here, a block here, a block here, etc. Then we break the periodic table up into sections. We've got this section. Now helium's the exception. We want to think of it as there. And then we've got this section. This section we call the S block, and this section we call the P block. So what we do to write electron configurations is you simply place the atom where it would be on the periodic table. For example, let's talk about boron. And to write its electron configuration, you start counting from the top, and you read to the right across each row, listing what you see until you get to boron. So in other words, we go through 1, we have to go through the S block, and we have to go through 1, 2 blocks. Then we go to the second energy level. We have to go through the S block, 1, 2 blocks. And then we get to the second energy level, the P area, with 1 block. So the electron configuration for boron would be 1s2, 2s2, 2p1. It tells you that boron's first energy level has 2 electrons in s orbitals, 2 electrons in the second energy level s orbitals, and the last electron is in the second energy level with 1 electron. Let's take a look at the whole periodic table and write electron configurations for a few. Alright, so let's say you want to write the electron configuration for phosphorus, which would be located there on the periodic table. Again, we start reading from the upper left, read across each block, each row, till you get to where you want to go. So let's start up here. We're going to go through the 1s block, and we've got 1, 2 blocks. Then we've got to go through the second energy level, the S block. We're going to go through 2 of those. The P block, 1, 2, 3, 4, 5, 6. So second energy level, P block, 6. Third energy level, we have to go through its S block, 2 of them. And then the third energy level, P block, 1, 2, 3, to get to where phosphorus would be. So what we would say is that phosphorus has 2 electrons in the first energy level in an s orbital, 2 electrons in an s orbital in the second energy level, 6 electrons in the second energy level in a p orbital, 2 in the third energy level in an s orbital, and the last 3 electrons in the p orbital of the third energy level. If we were looking at the Bohr model of the atom, that would be 1, 2, 3 energy levels, 2 electrons in the first, 1, 2, 3, 4, 5, 6, 7, 8 in the second, and then 5 in the third. But again, we don't want to think of it like that. We want to think of it in terms of orbitals as regions where we can find the electron. Let's do some examples then. Alright, let's take a look at some examples. The one thing, there is one trick that you want to realize, and that is when you get to that block there. If you notice, it says 3D. So in terms of order, we go 1s, 2s2, 2p6, 3s2, 3p6, 4s2, but then when you go into this region, which we call the D region, you drop down an energy level. So this block right there would be 3D1, 3D2, 3D3, 4, 5, 6, 7, 8, 9, 10, and then you go back to the 4 P's. So it goes 4s2, 3D10, 4p6, 5s2, 4d10, 5p6, etc. So again, when you're in the S block here, you're just in the period, but when you go to the D block, you drop down one, and when you go back to the P block, it's normal again. So the electron configuration for hydrogen, which is located there, would be 1s1. In fact, what you should do is turn off the vodcast now, try to write these electron configurations, and then turn it back on and listen to the answers. Okay, so I assume you did that, so let's go through the answers. So helium is located there, so that's 1s2. 1, 2. Beryllium, which is located here, would be 1s2, 2s2. Oxygen would be 1s2, 2s2, 2p4. My 4s always look like 9s. Magnesium, which is here, would be 1s2, 2s2, 3s2. Chlorine, which is here, would be 1s2, 2s2, 2p6. Calcium, which is here, would be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. I'm sorry, let me go back to chlorine. Let me go back to chlorine. I'm sorry, chlorine is here, third energy level. We have to add the 3s2 and the 3p6. Sorry about that. All right, let's take a look at iron, which is located 1, 2, 3, 4, 5, 6. So iron is going to go 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. Now we're here, so remember we want to go 3d, 1, 2, 3, 4, 5, 6. And then bromine, which is way over here, we're going to go 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10. Now when we go into the P block again, we go back to 4p6. And what I'm going to do is show you how to write this a little bit in shorthand so you don't have to write all of that. So what we want to do now is that we want to write these electron configurations in a shorthand version. So again, let's put chlorine where it goes in the third energy level. And now what we want to do, it's called the noble gas configuration. So instead of writing the whole electron configuration, what you do is you start at the element you're talking about and move backwards until you get to the previous noble gas. And in our case, that would be neon. So what we would say for chlorine is we would say take the electron configuration for neon, which would be 1s2, 2s2, 2p6, and then just tack on the last energy level, 3s2, 3p6. Those electrons are important electrons. We're going to refer to those as the valence electrons, and we've mentioned those before, and what they represent are the electrons in the outermost shell. Those are what we call the core electrons. But as chemists, what we're interested in is those, because those are the electrons that are going to be involved with bonding, and that's what this is all leading up to. Alright, so let's take a look at strontium. Strontium is located there. So the previous noble gas would be that one, which is krypton. So we would say, take the electron configuration for krypton and add 5s2. Let's take a look at palladium, Pd. That is located right there. So again, take the previous noble gas, which would be krypton, and then add 5s2, 4d, that would be 4d8. And then the last one, antimony, is located right there. So again, we would have krypton, 5s2, 4d10, 5p3. Alright, this might seem a little bit abstract at this point, and that's okay. What we're trying to do here is identify the valence electrons and the core electrons, because what we're going to do is use those valence electrons to describe bonding. Alright, let's just take a look at the last concept, and this vodcast is a long one, so let's do this last concept and then we will end it. Alright, now we want to look at electron configurations for ions. So remember, what we're trying to do is identify the placement of electrons in the atom. So if you have magnesium 2+, if you remember, magnesium normally has 12 electrons, but magnesium 2+ has 10 electrons. So its electron configuration is going to be the same as it is for neon. So we would say 1s2, 2s2, 2p6. If you're looking at an anion such as oxygen, oxygen normally has 8 electrons, but since it's 2-, it now has 10 electrons. So it would have the same electron configuration as magnesium 2+. When you have two particles that have the same electron configuration, we say they are isoelectronic. So for example, beryllium 2+ would be isoelectronic with helium. Okay, as with the vodcast on orbitals, what you want to do is the practice problems that are assigned. And again, as you do this more and more, this becomes much easier because it's all very logical based off of the periodic table.